Okay, why don't we go ahead and get started. Welcome to our December edition of the Statistical Seminar. Today we're going to talk about analyzing time-to-event data. And so I outline here in terms of what we'll cover is just basically talking about time-to-event and the basic concepts. Then we'll talk about probably most used method for analyzing time-to-event data, the Cox proportional hazard regression. And then I want to talk about the situation where we have multiple events, that is multiple events per patient. And then I want to also discuss a bit about competing risks and what that involves. And then I want to end up with a summary of the regression models we've talked about the last couple of months. So in time-to-event data, or it's probably more well known as survival analysis in medicine, in manufacturing and industry, it's known as failure time analysis. But basically, we have, in this type of analysis, two outcomes. We have an event, which is a dichotomous event, either you have the event or not. And then you have time, which is a continuous variable, the time frame in which you observe patients and whether they have an event or not. An event is also, you might see, particularly in the heart and vascular literature, what's called a composite event. And this is several different events, but if you have any one of them, it's considered an event. So, for example, you might have non-fatal MI or non-fatal stroke or a cardiovascular death. So if you have any one of those, you have an event. If you have none of them, you don't have the event. And then as far as time is concerned, we need a start time and a stop time. In time-to-event analysis, we can account for what's called censoring. And that is when we don't know the exact survival time of a particular individual. Then, of course, from a statistical standpoint, what we want to do is compare the survival functions of two or more groups. And then we can also, we have methods for assessing the impact of covariates on survival or the time to an event, like sex, age, diabetes, or other clinical variables that might impact survival. So I want to discuss censoring a little bit so that we understand what that is. So censoring occurs when a subject is observed for some period of time without the event of interest occurring. And so it's a patient, if death is your event, then they are followed up for some point of time without death occurring, or if you're doing maybe like cancer research, a recurrence of cancer. The basic assumption here is that the censoring process is independent of the failure event process. And there's different types of censoring. The one that you will see most often in the literature is what's called right censoring. And right censoring can occur for a number of reasons. Patients could be lost to follow-up, or maybe they withdraw from the study, or the study comes to an end without a patient experiencing the event. Or it might be that the patient dies from a cause other than the particular study outcome. If you're interested in cardiovascular death and death from some other cause, might be considered censoring. So let me give you an example here of right censoring, what we mean by that. So here we have several patients, the time from the start of the trial. So time is on the horizontal axis here. and then we have a point at which the trial is terminated. So for example, our patient number 1 here is observed, starts at the beginning of the trial and is observed throughout the entire length of the trial without any event occurring. So in that case, that patient is right censored. The second patient here starts at the beginning of the trial and is followed for a certain amount of time and then experiences the event. And then other examples here, you can see that the fourth patient here enters the trial, not at the beginning, but at some point into the trial. And they're followed from that point of time on, in this case, to the end of the trial without experiencing an event. And then patient number 5, for example, here is a patient who enters after the start of the trial and is followed then again for a certain amount of time and experiences the event. And then a few others that I want to point out here. These patients here start at a different time point, and then they're followed to the end of the trial. And so, for example, the point here is that when the trial ends, so does counting events or non-events. So for example, patient number 10 here comes to the end of the trial without experiencing the event, but sometime later after the event, they experience the event. However, that event is not counted in the analysis because the trial came to an end. We only followed patients up to this point. So that's what right censoring involves. And a major point here is that patients can enter the study at different time points. But when we go to do the analysis, each patient entry time is set to 0. And so their survival time is from whenever they started, whatever that might be, to whenever the event occurs or whenever they're censored. And so on the horizontal axis here, you can see that we have, for example, years from enrollment, or it might be years from randomization, or years from whenever if they were undergoing some procedure was done. And the time here can be, it's usually expressed in years or months. Once in a while, it might be days. And when we analyze this data, if the patient experiences the event, we code it as a 1. If they have no event, we code that as a 0 for analysis. So the other types of censoring are interval censored and left censored. In interval censoring, the event is known to have occurred in an interval of time, but we don't know exactly when. And left censoring is a situation where we're uncertain when the beginning of the at-risk time is, or when the patient is, what point the patient becomes at risk. And so in the first example here, patient number 1, you can see that the dotted line here represents time when this patient is unobserved. In other words, we don't know what is happening, but except that at some point in this time frame, the patient was at risk. And then at this point, we observe the patient, we follow the patient, and then they experience the event. So that's what left censoring means. This patient number 2 here is an example of interval censored. So we are observing patient number 2 up until this point in time, and then for whatever reason, we don't observe the patient. And then at this point, we begin observing the patient again. And then we know that the event occurred at some point in this interval, but again, we don't know exactly when in the interval, but we know it was between this time point and this time point. So as I mentioned, most of the literature that you'll read, at least in the medical literature, will be data that data that is right censored. Okay, so the survival function is just the probability of surviving longer than some time t. And so if S of t is our survival function, then it's basically the probability of at a point in time t of surviving longer than that. The hazard function is also an important function that we calculate, and in fact the two are related, the hazard function and the survival function. And the hazard function is the probability of an event at time t. So that's what is also known as the instantaneous failure rate. And usually this is plotted as the cumulative hazard function up until time t. So as I mentioned, the survivor function defines the probability of surviving longer than time t. The hazard function is the probability of the event occurring at time t. And the hazard function is the derivative of the survivor function. So if you know one, you can calculate the other. So let me illustrate how we calculate the survival function. And this is known as the Kaplanmeyer method of calculating survival. And so in my data here, you can see that I have a point in time that patients are observed, the number of patients at risk, then the number of deaths that occur at that point in time, and the number that are censored at that point in time. Or this could also be an interval. So the second to last column here is the probability of surviving. And that's calculated as 1 minus the number, in this case, the number of deaths divided by the number at risk in that time period. And then the last column is the cumulative probability of survival. And how do we calculate this? Well, it's just the cumulative probability at the preceding time, and then you multiply that by the next probability of survival. So in this case, for example, at time 0, the probability of survival is 1 because nobody is dying at time 0. And so we have 74 patients at risk, so the probability and the cumulative probability at that point is just 1. That's 1 minus 0 over 74. So in the next time point at 7 months, we have 1 death. So the probability of survival is 1 minus 1 over 74, 0.965. And so you just multiply the preceding cumulative probability by the probability in the next time point. And so that's what you get when you multiply, obviously, 1 by 0.9865. And so we continue that way. So in time 11 months, we have now 73 patients at risk because we lost 1, and we have 1 death occurring. So the probability of death now is 1 minus 1 over 73. And so then we multiply that by the preceding cumulative, and we get that, we get this number, 0.973. And so we continue like this all the way through our table here. And so we come out with our 3-month survival being almost 80% for this particular cohort. So that's the way that the Kaplanmeyer survival function is calculated. It's fairly straightforward. And then we can plot the survival functions. And so this is sort of a typical survival plot here, where again, the horizontal axis is always our time variable. And then our vertical axis is the proportion surviving, which range from 0 to 1. And so obviously everyone starts out with 100% survival. And then from there, it decreases depending on the number of people that experience an event. Now, in my example here, we have a kind of an issue with a real imbalance in the number of patients in each group here, chest radiation or no chest radiation. So that's kind of a problem, but it illustrates the Kaplanmeyer survival curve when it's plotted, and you get this stair-step kind of plot here where when there is a decrease, that means an event is happening. When there's a horizontal part of the curve here, means that there's no event occurring, although there could be patients who are censored at this time. And then here we have another event, and so on. For the larger group, the no chest radiation, it's really hard to see because there's so many patients in there, but it would, if we could kind of focus in on a small portion of this, we would have the same stair-step effect. And then we can then actually compare these survival functions. Usually what you see is a comparison with the log rank test. Okay, so here's another example with 3 groups, warfarin, aspirin, and then no medication at all. And now you see we have a bit of a different pattern here in that these 2 survival functions, the no treatment and the aspirin, cross here. So when you see that in a graph, that means that the proportional hazards assumption is not the case. In other words, you have non-proportional hazards, which if we took just the warfarin and the aspirin, we could see that these 2 survivor functions don't cross. So that would give us an indication that we have what's called proportional hazards. So there's different tests depending on whether the hazards are proportional or not. If they're not proportional, then there's different tests that you can use that accommodate that. And there's a statistical test you can do to determine whether the hazards are proportional or not. But the easiest way is just to look at the plots, at the survival plots, and see if they're all more or less parallel or if they're not parallel. Okay, another way that you might see this presented is by looking at the hazard rates, or in this case, then it's kind of sort of like you flip the survival curve around, and now you're looking at the hazards over time. Say I have 2 groups here, and in this case, then the better survival, or the least or the group with the smallest hazard rate in this case is the naproxen group. So you can see that the hazard rate here is smaller than for the other group here. So this is if particularly you're interested in an event, you're comparing groups and have an event. You'll see this typically presented in the literature. So as I mentioned, when we compare statistically survival curves or survival functions, the log rank test is one that's most often used, but it does assume that proportional hazards. There's a couple of other tests that you can use if the hazards are non-proportional. The Wilcoxon test places greater weights on events that are closer in time to the beginning of your study. And then the Flemington-Harrington one is more robust in that you can devise weighting schemes for events that are either nearer to the starting point or events that occur later in time. Okay, so then what's usually most important in survival studies is looking at how covariates may affect survival. And so just as we did multivariable linear regression and multivariable logistic regression, we can do multivariable survival analysis. And to do this, we use what's called, or typically is what's used as Cox proportional hazard model. And so maybe you have some covariates like smoking or diabetes, hypertension that contribute to the time or to the survivor function. And so in this case, what we have is the survival function is is a function of a matrix of covariates. And so the way that this is calculated, you have a baseline survival function here where there's no effective covariates, and then you just exponentiate that by the regression formula that you get. And you can see that this is similar to the linear and logistic regression that we looked at before, where you have a equation where in this case, the betas represent the regression coefficients and the x's the particular variables or covariates. And when we solve for this equation and we get the regression coefficients here, if we exponentiate those, then those are what are called hazard ratios. So our model, just as with linear and logistic regression, our predictor variables or our covariates can be either continuous or categorical. But in Cox proportional hazard regression is actually what's called a semi-parametric model, because we don't really have to know the baseline hazard rate. And we can still calculate the coefficients for each covariate and therefore the hazard ratio. It was just the exponent of the coefficient. But again, as the name implies, it assumes that we have what proportional hazard assumptions, or it's also called multiplicative risk. If you don't have, if the proportional hazards assumption is not met, you can still do the analysis either by including interaction terms, which I'll give an example of, and then, or we can stratify the analysis. So maybe we can stratify by, say, sex, or we can stratify by age, or some other covariate if we don't have proportional hazards. Okay, so the hazard ratio is a measure of how often a particular event happens in one group compared to how often it happens in another group over the time period that we're interested in. Or hazard rate is represents the change in hazard rates for every 1 unit change if the covariate is continuous. So for example, if the covariate is age, which if we analyze that as continuous, then we can also calculate a hazard rate for every increase in 1 unit or 10 years of age or 5 years of age, whatever we wanted to express that in. And just like in logistic regression, when we have an odds ratio of 1, that means there's no difference in the odds. Here, a hazard ratio of 1 means there's no difference in hazard rates between two groups. On the other hand, if you have a hazard ratio greater than 1 or less than 1, then that means that survival or the hazard rate in one group was better or worse in one of the groups. Okay, so here's an example from a study where the interest was looking at cardiovascular event, which was a composite event in this case, I believe. And the primary interest was looking at sex and race. And so we have our, in our analysis here, our hazard ratios. They're 95% confidence intervals and then a p-value. But so, for example, the way that we would interpret this, here, female is a reference group. So this means that when the hazard ratio is 0.75 for males, that means that the hazard ratio for males was 25% less than it was for females. For race, and this is just comparing African American versus white, there is virtually no difference in the hazard. Their hazard ratio is almost 1. So, but what we were interested in was looking at if there's an interaction between sex and race. And so it turns out that this is the case, that there was a significant interaction, which I'll show a picture of that in a minute here. And so then we also had a number of covariates that we thought might also influence the survival rates or the hazard rates. So, for example, age. Here we've expressed this in 10-year increments. So here a hazard ratio of 1.28 means that for every 10-year increase in age, there's a 28% increase in the hazard rate. And then BMI, for example, is the sort of the opposite interpretation. Here for every 5 unit increase in BMI, the hazard rate is actually about 8% less. So the interpretation here is very similar to what how we interpreted an odds ratio. And so you can see there's others here. Acute MI, diabetes have a fairly negative impact on survival. And remember, in our multivariable analysis, each one is adjusted for all of the others in the model. And so here is a plot of the data by sex and race. And what I've done here is I've plotted the cumulative hazard rates and I smooth them out. So it's a little easier to see rather than having the Kaplanmeyer stair step there. So you can see here where we get the sex by race interaction, in that the cumulative hazard for white males is quite a bit smaller or less than it is for the other 3 groups. And so here the black males have the highest hazard. Females are fairly similar here. In plotting it this way, we can sort of, or we can see the interaction between sex and race the cumulative hazard for white males is quite different from the other groups, and that's why we're getting our interaction. Okay, so what I want to consider next is looking at multiple events. And so most of the primary analyses that you see in the literature only consider time to the first event, but many studies have multiple, and of course they would have to be non-fatal events. And sometimes that's ignored, sometimes it's analyzed as a secondary analysis and looking at the multiple events. And so there's different methods for handling multiple events. I've listed 3 here: the Anderson, Gill, Whalen, Weisfeld, the Prentice, Williams, and Peterson. The issue with the Anderson-Gill ones that it assumes that events are independent. And that's probably not really a valid assumption, because if you have one event, say like you have a non-fatal stroke, then one would think that that probably increases the probability of having a second stroke. So the other two here, also referred to as the marginal risk set and the conditional risk set, don't assume that the events are independent. And so the one that we use most of the time in the analysis we do is the last one, where we look at the conditional risk model. And basically what that does is it orders events in time, which stands to reason that if say your non-fatal event is stroke, then your second stroke can't occur before your first stroke. So we have an order of events that we set up in our data. So I'm going to use an example here from the data that I used last time from the HCMR data. And we looked at the outcome of atrial fibrillation. And last time I just used it as an example of logistic regression. I ignored the time factor, but obviously from the entry into the study to the time, there would be time to the AFib event. And of course, in this case, we have multiple events for some of the patients. So it turns out that we had a total of 127 events among 96 patients. And then we had a large number of potential predictors, demographic, clinical, morphology, and so on, that I talked about last time. And we had some, I think, of 2,300 and some patients. So only 96 of those actually had an AFib event, but some of them had more than one event. And so here's what the multiple event data would look like. And this is just some data I've made up here. But so patient one, we have an entry point, which is 0, an exit point, which is the length of time they've been followed. So in this case, it's 36 months. They had no AFib event. And then I have just a couple of the covariates that we were interested in looking at here. And so patient number 2 here enters at time 0, and at 14 months, they experience an AFib event. Then the same patient, the next entry time would be 14 months, and then they had another AFib event at 37 months. And so you can see that the way we code this would be entering the order of the events here, or we're going to stratify by the event sequence here. But you see that the covariates, unless we have time varying covariates, they're going to be the same regardless of which AFib event it is. And so patient 3 here has 4 events. They enter the study at time 0. They have an event at 22 months, another event at 42 months, another one at 56 months, and a fourth one at 62 months. And so again, this is the way that we've designated this in terms of stratifying or ordering the sequence of events. And again, as you can see, the covariates in this case would remain the same. Obviously here, age is the age at entry. We could calculate this as age is a time varying event, but that sort of complicates the model. Okay, and so here's sort of some graphs of, in this case, looking at the observed AF-free functions, or the atrial fibrillation-free functions, because here we're not looking at survival, we're looking at being AFib-free. And so we, in this case, what I've plotted here is our observed survival functions, and then our predicted survival functions predicted from our model that we looked at. And some of the variables that we had in the model were dyspnea, the LA volume, contractile percent, and BMI. And so in this case, you can see that the observed and predicted are fairly similar. There's some differences you can see here, but it's more as we get more towards the outer or to the longer follow-up times. So this gives us a pretty good idea that our model is predicting well when the observed and the predicted are similar. And if you remember when we looked at the logistic regression, we had the same sort of idea here of calibration of how well the predicted and the observed line up. Okay, then what I want to focus on next is the concept of competing events or competing risks. And so now we have multiple events, but they're actually different events. And the competing event modifies the estimation of survival function of the event of interest. And so in our HCMR study of atrial fibrillation, death was considered a competing risk. If we were looking at in chronic kidney disease, time to dialysis, then death would also be a competing risk. And that's the concept here is that the competing risk, patients are not in the study anymore, but so that's going to affect the survival function or the hazard function of your event of interest. So, and sort of diagram it this way, where we have patients without any initial event, and then they could either, the event could be either atrial fibrillation or they could die. So death in this case would be a competing event. Now it's possible that you can have more than one competing event. So it gets more complicated as you do that, but that is a possibility as well. And so there's different, well, I guess I should say for analyzing competing risks, there's competing methods. The one that you'll see used most often is the fine and gray method, where they calculate a subdistribution hazard function to adjust the hazard function or the survival function of your event of interest. The other way that it is sometimes argued is actually a better way because of what the fine and gray method involves, is just to censor those patients who have the competing risk. So if, for example, if death is a competing risk, then we would just censor those patients at death. It would be just like someone who dropped out of the study or was lost to follow-up. And so there's some argument in the statistical literature about what is best to do. So of course, in our study, we did both. In our HCMR study, we did both. And so this is what we found when we did the competing risk model, and then we just use it without the competing risk model, where we just used death as a censored event. And so in this case, what you see is that there's very little difference in the hazard ratios between the two methods. In fact, most of them don't differ until at least the third and fourth decimal places. So in our situation here, in our study here, there was no no real reason to use the competing risk model of fine and gray. We just censored observations at death because we got essentially the same model. Now that's not always the case. That won't always happen. And in our study, it may be because we had very few deaths. In fact, I think there were 24 deaths out of the 2,300 or so that we had in our study. But as I say, you want to look at this because in some cases it doesn't really make that much difference, and it's much easier to analyze the data and make sort of more straightforward conclusions if you just use your competing risk event as a censoring event. Okay, so I want to end up here with summarizing what we've talked about in the last 3 sessions here. We started out with linear regression. The predictors or the covariates in the model can be either categorical or continuous. Our outcome, we assume, is normally distributed, although it doesn't have to be exactly normally distributed. And there's no concept of censoring. The same is similar with logistic regression. We can have predictors that are categorical or continuous. In this case, our outcome is binary. However, we can also do an analysis where the outcome is categorical, and so we can do either ordered logistic regression where your categories are ordered, or we can do a multinomial logistic regression where they're not ordered. But again, there's no concept of censoring. So in survival analysis that we talked about, again, if we want to do a multivariable model, our predictors can be either categorical or continuous. But now we have 2 outcomes to consider. We have the binary outcome of the event, yes or no, and then the variable of time. And now in survival analysis, we're going to consider censoring. That is, we can use the data from all patients, regardless of whether they complete the study or not. And so in terms of models, recall that our linear regression model can be expressed as the dependent variable, or the outcome, is equal to, in what I've used here is alpha plus beta x, where x is our covariate, or our model, or our variable of interest. And the beta is the regression coefficient, which for linear regression is essentially a rate of change. In other words, it's it gives you the change in y, or the dependent variable, for every unit change in the covariate, or the independent variable, in this case x. And alpha here I've used as the constant term. In other words, that's what y equals when x equals 0. In logistic regression, we have a similar sort of thing, except that now we're looking at the logit, or we're looking at the probability of an event. But we have the same kind of formulation here. But now what we're interested in is the odds ratio. In other words, the odds of one event divided by the odds of, or the odds for one group, or one variable divided by the odds of another group, or another continuous variable. And so in our logistic regression equation, if we exponentiate the beta coefficient, we get the odds ratio. And then survival analysis, as we just talked about in terms of the hazard ratio, in this case, we have our regression equation, just like we do in the other 2, in linear and logistic regression, except now if we exponentiate the beta coefficient, we get the hazard ratio. The hazard rate of one group divided by the hazard ratio of another group, or if we have a continuous variable, the change in hazard for every unit change in the independent variable. Okay, so let me just finish up here by kind of reviewing some of the key points about building regression models. So if we're doing, if we have a large number of covariates and we're interested in predicting our outcome, then we can use penalized regression as probably the most appropriate way to build a model and select variables. And we talked about how to do that primarily with logistic regression, but you can do penalized regression with linear regression or with survival analysis as well. And then remember that what we're interested in is the model. It's the combination of predictors or variables in your model that do the predicting. It's not whether an individual predictors are statistically significant or not. Because as we saw when we did the logistic model, there were some in our best model, there were some individual variables or covariates in there, predictors in there that were not statistically significant all by themselves. And then, of course, you want to evaluate your model, how good it is. And in linear regression, we looked at the concept of R squared, the percent of variance accounted for in the dependent variable by the model. And then in logistic regression, we looked at discrimination, calibration, and those are the same sorts of things that you would want to look at in survival analysis as well. And basically, it's the idea is, well, how well is your model predicting? How well does the model fit the data? Okay, so just to mention for survival analysis that many of you may be familiar with, in SAS, the function phreg will do, I think, virtually all of the different models that we've talked about in terms of survival analysis. In Stata, STCOX and STCR reg, it's competing risks for the last one. And then there's probably a lot of functions in R. I just mentioned one here, COXPH, which you can use to do survival analysis. So again, I want to thank you. Oh, right, one more slide here. I have some references here that are on the will be on the recording, and you can look at those. The first two are probably the easiest to read. The other ones are more technical. So thank you for your time. If you have any questions, I believe we can use the Q&A. Let's see if I can get to that here. Okay, let's see here. Okay, so one question was, I'm not sure how you analyze different events occurring in different individuals at different time intervals. So let's assume this is talking about competing risks. So the way that the fine and gray method works is to compute the what they call the subdistribution hazard. And so this is applied every time that you do the calculation for a particular interval. And it's so a patient might have typically only has an event of interest or a competing event of interest. So that's fairly simple. It's more complicated when you have a situation where, say, a patient might have a non-fatal event, and then afterwards they have the death or the competing risk event. But it's analyzable and I mentioned the interpretation of can be quite not necessarily difficult, but it might be a little more complex. So a second question was the relationship between cumulative incident function, survival, and hazard function. So as I mentioned, the survival and hazard functions are related. The survival is the probability of surviving past a particular time point. The hazard function is the probability of dying at the particular time point. The cumulative incident function is looking at just the occurrence of events and how they occur over time. So it's like it's counting the events and just calculating how the events accumulate over time. If that doesn't really answer it very well, I'll try and find a better explanation of that. But the in competing risk, what's calculated is the cumulative incident function, and that is for the competing event, and then that's used to adjust the survival hazard and hazard functions of the event of interest. Okay, as I mentioned, this is being recorded, so if you'd like to listen to it again, or if you have any questions, please feel free to email me, which let me share my screen again here. Yeah, so again, if you'd like to email me, you can do so at MedStar. So again, thank you for your participation. Thank you for your interest, and we'll continue again after the first of the year. My next presentation will be, I'll give you the title right now. It's How to Really Lie with Statistics. It's about meta-analysis. Anyway, we'll see you again after the first of the year. So happy holidays, everyone.